Hello, I'm Cusick Park, a PhD student at University of Wisconsin-Madison. And in this talk, we will present a data-driven reduced order modeling of geometrically nonlinear structures based on a Gaussian process regression. So our study focuses on geometric nonlinearity, which can be typically found in the thin structures of advanced vehicles when they are subjected to severe aerodynamic or aerothermal stresses. The finite element models function as digital twin of geometrically nonlinear structures to simulate various types of nonlinear responses. But the FE methods often require a tremendous computational overhead for integrating the nonlinear responses, so it brings a need of using reduced order models. A reduced order model, or a ROM, is a simplification of FEM that significantly reduces the degrees of freedom by projecting the full order equations of motion onto a smaller model subspace. Many research have revealed ROMs can accurately simulate the dynamic responses with a dramatically reduced computational time. The method includes enforced displacement methods and implicit condensation and expansion method, which can be referred as ICE in this study. The ROM techniques are known to work very well to many applications. However, there still exist some issues that we need to care about. First, a single ROM only represents a single FEM configuration, which means the ROM does not account for the variation of FEM parameters. Thus, as any FEM parameter changes, the corresponding ROM must be recomputed for a Galerkin projection using a new set of static load displacement solutions. So this might make the ROM-based simulation quite repetitive and tedious. Second, the number of nonlinear terms in a ROM increases cubically, but not every term contributes equally to capturing the nonlinear responses. So such redundancy makes computational cost demanding, particularly when the ROM is used for the model updating task. And lastly, some of the ROM coefficients tend to be sensitive to how the static load cases are prescribed for the Galerkin projection. And consequently, the accuracy of ROM is not consistent to the different sets of load scales or load cases. This hence weakens the robustness of the ROMs. So the objective of this study is to propose a new data-driven ROM method for geometrically nonlinear structures that addresses these challenges. Our approach trains a regression ROM with a collection of varying FEMs, such that the ROM can incorporate the variation of FEM parameters. This implies that the physical intuition that FEM entails can be transferred to and embedded in the ROM. So this will eliminate a need of repetitive ROM computation, because once the regression ROM is trained offline, one can directly predict a ROM from any new FEM configuration within the range of the training data set. Also, in this work, a Gaussian process regression, or GPR, is applied for the data-driven ROM, which enables ROM to evaluate the uncertainty of the ROM parameters with respect to the applied loads. Then the uncertain or sensitive nonlinear ROM parameters can be efficiently filtered out using this function provided by GPR. GPR has been acknowledged as a powerful regression tool to define a finite collection of variables based on a Bayesian approach. The GPR method specifies a regression model by its mean and covariance functions, and so is non-parametric and flexible toward either simple or complex problems. One of the strengths of the Gaussian process model is that it quantifies the predictive uncertainty of the model with respect to the input variables. So in our approach, the GPR is applied to the training sets of FEM and the corresponding ICE ROMs. The input training sets are NTR input FEMs with varying parameters, and the corresponding output sets are the sets of linear and nonlinear coefficients in the ICE ROM. Based on the assumption that the collection of ROM coefficient y obeys the joint Gaussian distribution, the GP model can be described by the function of mean and covariance, and the model can also account for the independent noise that corrupts the distribution of the given training sets. Then the GP model can be trained by optimizing the hyperparameters and its mean and covariance functions by estimating the maximum likelihood of the model with respect to the training sets. Then the distribution of the training sets can be used as a prior from a Bayesian perspective, and the posterior distribution for a new test set can be estimated based on the conditional distribution of joint Gaussian variables. Then the mean and variance of the ROM coefficient can be easily estimated for any given set of FEM parameters within the prescribed range. The GPR ROM captures the variability of the FEM parameter sets and quickly predicts a ROM and its predictive uncertainty with respect to a new input FEM parameter set. The GPR ROM can be efficiently trained by the proposed algorithm, which utilizes the fact that the GP model can estimate the predictive uncertainty. That is, we apply the random forcing FR when computing the training sets of the ICE ROM. Then each ROM coefficient model can measure the uncertainty or variance of that coefficient with respect to the random forcing FR. So if GPR ROM coefficient is certain with respect to the low scaling, then these will be kept in the ROM. On the other hand, if the sensitivity ROM coefficient, the sensitive ROM coefficient is uncertain, it will be filtered out from GPR ROM because they weaken the robustness and potentially lessen the accuracy of the ROM. So based on using the algorithm here, we expect to define the optimal or minimal sets of coefficient in the ROM. In this work, the GPR ROM approach was tested on two thin beam structures that are well known to exhibit geometric nonlinearity. The GPR ROM was first applied to a flat beam model, which has been studied in many prior works. In this case study, a GPR ROM incorporates the variation of boundary stiffness, here Kx, which would be one of the most uncertain parameters to model the beam structure. So a wide range of the boundary stiffness from soft to nearly clamped was considered. And within the given range, the variation of the stiffness significantly impacted the nonlinear coefficients. Then 20 training sets were uniformly sampled within the bounds, and the reduced basis of the GPR ROM included mode 1 and 3, forming a 2DOF GPR ROM. The random low scaling factor was applied within 0.25 to 0.75 times of the implicitness. Then the trained GPR ROM was evaluated by 900 uniformly distributed test sets. So these figures here show the predictive mean and the 95% confidence interval of the GP model of each nonlinear coefficient. It turned out that all the quadratic coefficients are very uncertain and have large variances centered around the zero. The predictive standard deviation of the nonlinear coefficients are presented in these tables, and the values also support the significant uncertainty of the quadratic terms. The quadratic terms were very sensitive to the force scaling factor and did not contribute to characterizing the ROM with respect to the variation of fan parameters. So they could be considered to be redundant and removed from the ROM. So this is as expected, as the geometric nonlinearity of a flat symmetric beam is known to not contain any quadratic stiffness effects. And on the contrary, the cubic coefficients here were very certain with respect to the random force scaling and were observed to change smoothly from small to large values as the axial spring stiffness varied. So the GPR ROM algorithm removes all the quadratic terms while keeping the cubic terms in the filtering stage. So then the mean predictive standard deviation of the GPR ROM significantly reduced here, and the confidence intervals of the cubic terms remained the same, indicating that the ROM became small but robust with respect to the force scaling factor. The GPR ROM could be further filtered to have only 6 nonlinear coefficients in total, and we could find a slight increase of uncertainty for the cubic terms. This implied that the robustness of the GPR ROM has started to decrease. And if one seeks to reduce the number of GPR ROM coefficients further to 4, the uncertainty would increase even more as found in these figures. The accuracy and robustness of the GPR ROMs were evaluated using their nonlinear normal modes, or NNMs. And the GPR ROM could estimate the variability of nonlinear responses for a wide range of boundary stiffness. The NNM curves closely matched the reference NNM of the full fan. And that was when the number of nonlinear coefficients was equal to or greater than 6. And it started to break down when the number of nonlinear coefficients, NNL, was equal to 4. The error from the reference curves was relatively small, especially for the third NNM. And this was because the flat beam entails relatively weak modal coupling. We also investigated the confidence intervals of the GPR ROMs for predicting the NNM. And the plots show that the confidence intervals dramatically increased from NNL equals 4. This highlights the trade-off between having highly certain prediction and reducing the size of the ROM. It can thus serve as a powerful indicator for defining the optimal ROM coefficient set, depending on whether one is more interested in robustness versus computational efficiency in the application in question. We also tested GPR ROM on a curved beam model that exhibits more complicated nonlinear behaviors, such as snap-through instability. The design parameters for the GPR ROM were chosen with the Young's modulus and the radius of curvature because they entail significant uncertainties due to the manufacturing variability, and they also have a significant effect on the dynamic response. The range of both of these parameters were taken to be from 50 to 150% of their nominal values. and 10 uniformly distributed samples were selected from each parameter, and they were combined to construct 100 training sets. The training sets were then used to train a 3DOF GPR ROM consisting of modes 1, 2, and 3. Compared to the previous flat beam example, the complexity of the GPR ROM model was exponentially increased by incorporating two-dimensional design variation of them and having a three-mode basis in the ROM. So this resulted in a significant increase in the total number of steady load cases. The random forcing scale range was chosen wide enough to sufficiently capture the nonlinear dynamic behavior of the curved beam and large deformations. The results show that the linear and nonlinear coefficients are more sensitive to Young's modulus than the radius of curvature. The linear frequencies were very accurately predicted with almost no variance, while some of the nonlinear terms had large prediction variance, especially for most of the non-resonant terms, and this will align with the fact that the non-resonant terms contribute less to capturing the nonlinearity of the system. The curved beam GPR ROM was trained through the proposed framework, and after 7 iterations, the number of nonlinear coefficients reduced from 48 to 21. The mean predictive STD of GPR ROM also substantially reduced, indicating that GPR ROM became much more robust as the size was reduced by more than 50%. In this case study, we applied 5 different force scaling bounds to train the GPR ROM, and the predictive STDs of resulting optimal GPR ROMs are presented in these tables. The results reveal that the uncertainty of the GPR ROM tends to increase as the force scaling range increases. But it was interesting to see that the nonlinear coefficients kept in the GPR ROM were mostly the same between the different cases. This means the GPR ROM was robust enough. So even when the GPR ROM was computed using a smaller force scaling, it was able to evaluate and distinguish relatively uncertain coefficients from the certain ones in that ROM. The unending curves of the GPR ROMs are shown in these figures, and the GPR ROMs accurately captured the nonlinear responses propagated from the design variation, ranging from ER min to ER max. Interestingly, the softening hardening behavior at ER min turned to pure hardening at ER max, a feature that is captured by the GPR ROM. The accuracy of GPR ROM was preserved even when reducing more than 50% of the original number of nonlinear coefficients. And this reveals that the three-mode ROM contains a significant number of redundant coefficients, but GPR ROM can neglect these terms and still accurately capture the nonlinear responses. The predictive uncertainty of the NNMs also suggests that the GPR ROM having fewer than 21 terms begins to increase the uncertainty in the nonlinear response. This again highlights the utility of using the GPR ROM in that they predict confidence intervals of the nonlinear responses, such as these NNMs. The case was also used to evaluate the computational efficiency of the GPR ROM and to compare it with that of a full FAM and a typical ICE ROM. The offline stage for training GPR ROM required a relatively high computational cost, and this was due to computing a large number of steady solutions. It is important to note that this stage is entirely offline, and if resources are available, it can be parallelized with perfect efficiency because each static locate is independent of each other. In the online stage, the GPR ROM could quickly generate an ICE ROM in less than a second for any given set of FEM parameters, while ICE ROM approach needed to newly compute the static data to create a corresponding ROM. The GPR ROM was also tested to integrate the random responses, and it was revealed that the computational efficiency was the same as that of ICE ROM. So they were orders of magnitude faster than integrating the full FEM. So our GPR ROM approach utilized the governing physics of the problem and utilized the form of polynomials in the dominant modal coordinates such that they can efficiently capture parameter variation in the FEM. The GPR ROM could accurately capture the variations of FEM design parameters with an optimally reduced set of nonlinear coefficients. When the FEM parameters were known to be uncertain, then we could use the GPR ROM to efficiently compute the variability in the response due to the known distribution of those FEM parameters. Also, the computational efficiency could be greatly enhanced by completely decoupling the offline and online stage. We are currently working on exploring GPR ROM application to nonlinear model updating by employing these key benefits of the GPR ROM. We also plan to apply this machine learning-based ROM approach to thermal model updating, which entails a significant amount of uncertainty in it. Yeah, so this was all we had, and thank you for your attention.